Hello and welcome back. If you weren't with us yesterday, I'm Dr. Swope and I'm from Northwest High School, and that means I have to say, let's go Jags. So let's continue with our virtual review for AP Psychology. Today, what we have on is basically statistics. We're going to look at, we got three major divisions we're going to do. The first one is to distinguish the purpose of, it's a fancy way of saying, we're going to tell the difference between what is descriptive statistics and what is inferential statistics, okay? And then the second thing we're going to look at is apply basic descriptive concepts, statistical concepts, basically looking at graphs and calculating simple descriptive statistics. And let me pause right there. On the AP Psychology in years past, and especially probably in this year coming up, you will not need to calculate any difficult math concepts. And that's, people get intimidated when we talk about statistics, but the reality is everything should be relatively easy. You're not going to need a calculator. So, deep breath there if math is a little bit intimidating for you. Okay, another thing, and notice I put this in all caps. This is something you might want to take advantage of or jot down. 47%, well, you don't need to know, 47% roughly of all statistics are made up on the spot. And so, I really wish, believe it or not, the joke is, of course, that's made up. So I wonder how many of you in the last second were furiously writing that down. And I really wish today's lesson fell on yesterday so I could make that a great April Fool's joke. But it's a good kind of launching pad to think about what is statistics, what do we use this, and why is it in a psychology class? Some people say, oh, I don't like math, I don't want, why is it here? Well, maybe today we can find out why we use statistics, or why they are part of an AP psychology class. Okay, as you know, before we jump into today's lesson, we've got to check in with our old friend, Mrs. Schmidlap. So here's where we left yesterday. Mrs. Schmidlap, of course, wants to do an experiment on whether watching educational YouTube videos will increase learning. And she wants to, you need to explain how the following terms apply to Mrs. Schmidlap's ideas for this research. So we've got four concepts. Let's go through each one of them. Remember, we're going to use the SOTAS model that Mrs. Fenton was so good to share with us and teach us about. We're going to look at the last three letters of the acronym SOTAS, and that would, of course, be define, apply, and synonym. So we're going to define the independent variable as something that an experimenter does. Remember I said yesterday, the independent variable is something an experimenter does, and the dependent variable is something the experimenter gets. And I put, for example, a gardener might give fertilizer as an independent variable to see if it affects plant growth. And I picked that example on purpose to show you that an independent variable in the scientific method aren't locked into psychology or any particular academic discipline. You can use the scientific method, independent variable and dependent variable in nearly any question. So that's our define. Let's apply. Mrs. Schmidlap's independent variable was whether the students watched educational videos. Okay, the synonym, going deeper, is Mrs. Schmidlap needs to operationally and precisely define watching videos. So what does watching videos mean? That's too broad of a category. Similar to the idea of what does doing homework mean? That's way too broad. So we need to operation define it so it can be measurable. She should say that students must watch at least 30 minutes. But if you're paying attention and you took some stuff away from yesterday's lesson, you could go even further and say, how do we operationally define watch? Does that mean just stare at a screen? What if you had windows within windows or multiple tabs open? So I think you're getting the idea that we need to operation define and go deeper. Demonstrate to the AP reader who's reading your FRQ that you know what you're talking about. Now we're going to define an operational definition. And an operational definition is an attempt to make an abstract concept such as learning observable and measurable. And we're going to apply it. Mrs. Schmidlap needs to operationalize the dependent variable of learning so that it can be measured. For example, she can define learning as the ability to earn 80% on a quiz. Okay, so now that's measurable, right? Now we're going to go deeper. And however, by operationalizing and simplifying a concept such as learning, which is broad and intricate and almost philosophical, she might be guilty of reducing learning to something that it's not. And as students across the country know, and teachers know, learning is far more than just scoring something on a quiz. So there's going to be the problem. I hopefully you can demonstrate that as you go deeper, as you discuss operational definition. We define it, we apply it, we give a synonym. Now we're going to look at confounding variable. We're going to define it as anything that might affect the dependent variable that is not the independent variable. Okay. And we're going to apply it in Mrs. Schmidlap's experiment. One confounding variable is whether students read a book in addition to watching the video. Maybe they learned enough to get that 80% from a different source, and it wasn't the watching the video at all that caused that. We're going to throw out another confounding variable. Might be that student motivation to learn. For instance, if students have the video or playing but do not pay attention, then their lack of attention might be the confounding variable that affects the dependent variable more than the independent variable. The fourth one we had was ethical considerations. And we're going to define it as, I actually kind of defined it as two different ways here, right? So ethical considerations are issues that might harm participants, and or you could define it as they are guidelines to help researchers construct healthy or positive experiments. We're going to apply it. Mrs. Schmidlap's experiment, she needs to be careful to make sure that she keeps student grades confidential and not publish them in her study. And so remember, confidentiality was one of our ethical considerations that we talked about yesterday. We want to prove and go a little bit deeper to the AP reader that we know what we're talking about. We're not just randomly defining and throwing out an application. Let's leave them no doubt that we know what we're talking about. So we're going to give another ethical issue would be informed consent. Did Mrs. Schmidlap let her students and probably their parents know, if they're minors, that their hard work might be used for her research in addition to affecting their grades? I mean, let's face it, the reason they watched the video and did the homework was to improve their grades and to learn, not necessarily to help her in her research or career ambitions. So that's the review of our homework from yesterday. And I hope that my explanations matched with what you did. And if you didn't really think about it at all until today, that's okay. There's always tonight. And again, watching videos, we're going to take a cue from Mrs. Schmidlap. Watching videos is good, but if you don't practice with it, then maybe you're not getting all you can out of your time. So let's move forward a little bit. And our lesson today is going to be statistics in research. Okay. And what we did, like I talked about before, let's talk about research. What the heck is it? And we're going to roughly define statistics as data exploration techniques. Okay, what does that mean? It's just simply a way to take large amount of data and turn it into information. Okay, so look at number 2. We're thinking statistics as a tool to help turn data information. Think of data as raw material, information as the finished product, right? Number 1, think about this. If you have a survey with 50 questions, okay, so we talked about that 2 days ago. We talked about surveys, and you want to see if there's a relationship between question 13 and question 27, or 27 and 43, or maybe just like with the ice cream and the drownings example, there's a third variable, question 13, 23, and 47. That's going to be a lot of variables, a lot of data. And we want to use precise statistical techniques to help us find the relationship and evaluate if those relationships are strong, or here comes the word, significant. Okay. What if you had an experiment with 500 participants? That is a lot of people. Okay. And you're collecting quite a bit of data about them, their height, their weight, their age. And so statistics are they're a tool. Don't think of them as something you have to do. Think of them as something you get to do to help make sense of your research work. And this might be familiar to students who happen to have different teachers who teach the same thing in a high school. A lot of teachers team teach, right? So 2 teachers give similar tests. One teacher gives a 37 question test, and one teacher gives a 43 question test. On the first test, the student earns a 34. On the second test, the student earns a 42. Who did better? So, I said statistics is a tool to help turn data into information. We might also say that statistics is a common language between research. It allows us to translate the specifics of one study with different numbers of variables into another study with different numbers of variable and kind of compare them apples to apples. So I hope that that explains why we do this. The two types of research, I'm sorry, two types of statistics we're going to get into today are inferential statistics and descriptive statistics. Okay, so right now, mentally make a note, we're going to kind of subdivide into two major categories today. Inferential statistics, ready? Can knowledge be inferred from a small sample to a large population? I'm going to reread that because it's really important. Can knowledge be inferred from a small sample to a large population? Now, look what I have in parentheses. This is the exact opposite in a way of what we were talking about with sampling yesterday. In sampling, it was all about taking a group, getting a small group from a large population. Now that we have the results, we're going to take the results from that small group and can we reapply it to the large population? So to sample, we go from large to small, and inferential, we go from small back to large. Remember that random sampling doesn't always lead to a representative sample. Yesterday, I gave the example of what if in a large high school or a small college, 3,000 people, you want to do research and you put out an advertisement and 50 people answer your call, and miraculously, they all happen to be female. But your college is co-ed. So just because you got a random sample doesn't mean it leads to a representative sample. So if the group you're working with, that small group you're working with, yields results, can you take the results of a small group of only women and then apply that to a larger group of a co-ed college? And that might lead to what we call research bias. It's going to lead to a problem. Can we infer that? And we'll dig into that later. Look at the third bullet point. If you were looking for a confounding variable, maybe in an FRQ, and you're kind of you just don't know what to write, here's kind of the old faithful. Most psychological research is done by university professors. And who are their participants? University students. I don't know the exact number, the exact percentage, but it's pretty high that most research is based on participants where their ages are 18 to 22 years old, closer to the 18-year-old, because a lot of research is done on college freshmen. Okay, and that sounds wonderful. A professor does research, they get 50 people, they found their conclusion. Can they then apply it to the larger group? And the question is, well, I'm not sure, because we talked about yesterday, the average age of the American population is 38. So there might be some built-in bias in nearly every university-based research. Inferential statistics and statistical significance. That is a mouthful. I'm glad I got it out without fumbling or slurring over that title. So let's talk about statistical significance. Ready? How sure are we that our result is what we think it is? It's not a type 1 error. How sure are we? Are we 100% sure? Well, we know philosophically that's pretty much impossible. Are we 95% sure? How about 90% sure? And you could imagine, if we had time, we'd slow down and ask, would you buy a car where you're 95% sure the brakes work? 90% sure? So would you accept research that you're only 90% sure isn't due to randomness or chance? Okay. The first bullet point here is, let's say that P represents the messiness. Ready? We could call it chance or error or a confounding variable. P is an average of all the things that mess up your experiment. And we talked about confounding variables yesterday. So we want small p. Okay, a p of less than 0.05 or p of 0.05. If p is bad, that means that there's a 95% chance that the study's results are not due to randomness, bias, or confounding variables. So the smaller the p, the higher the significance. Okay. I just said this, the smaller the p-value, or the p, is the more significant the results. So a p-value of 0.01 mean there's only a 1% chance that the results are due to chance or error. That's a 99% certainty. If your statistics yield a p-value of 0.01, that's really powerful. That's a really strong result. There can never be a p-value of 0 because nothing can be proven 100%, including this sentence. That's a fun one to think about. Remember, nothing's absolute except this sentence, or maybe including this sentence, depending on how you want to philosophically play with that. A p-value is the opposite of statistical significance. That's the takeaway here. P-value is the opposite of statistical significance. As p-value goes down, significance goes up, which brings us back to a negative correlation. Okay. Inferential stats, quick practice. Let's talk about a colleague of mine, Mr. Reed, taught one of his classes online and another one in person to see if there was a difference in test scores. He did some calculations and isn't sure if the difference between the results is significant. His p-value is 0.07. So my question to you, is the difference significant? Well, let's look. A p of 0.07 means randomness, chance, or confounding variables is 7%. That means his level of uncertainty is 7%. His level of certainty is only 93. So his conclusion, no, it's not significant. Pretty much standard acceptance is 95%. Some research studies have a higher standard of 99%, but for most research studies, we're going to go with if p is less than 0.05, then it's significant. Okay. Let's talk about this null hypothesis thing, and perhaps you've heard of it, and it does sometimes confuse students and even some teachers. Okay, so the null hypothesis, ready? Let's look at this and read it carefully, is it predicts that there will not be a significant relationship. So the null predicts that nothing significant will happen in your experiment, or that you cannot apply your results from the small group in your inferential statistics to your large group. Let's talk about the idea that professionally, scientists are skeptical people. Personally, who knows what they believe? But skeptically, scientists should say, you know what? I don't believe it until I see the numbers. See, they're going to assume nothing until they see the numbers, right? And maybe we could all take a lesson from that, I don't know, in social media or the news or something like that. You know, a headline splashes across and it's amazingly interesting and fascinating, but maybe we should be skeptical until we see the numbers, see the stats behind where they get to that big flashy headline. The goal of researchers is to disprove the null hypothesis, which in inferential statistics predicts the results cannot be applied to larger population. I'll say that again. The goal is to disprove the null hypothesis, which predicts the results cannot be applied to larger population. So the null basically says your p-value is going to be pretty big, and we want to prove the null wrong. Look at this handy dandy little table we have here. Okay, let's look at our 4 quadrants starting here. If the results are significant, which means they have a p-value of less than 0.05, and the experimenter thinks the results are significant, we can reject null. The alternative hypothesis, which means if independent, then we will get a significant difference independent. That means the study worked, okay? Now, if the experimenter thinks the results are significant, but the results are not significant, remember we talked about a type 1 error, or also called a false alarm error, okay? Now, down here to the bottom row, the experimenter thinks the results are not significant, okay? But the results actually are. It's a type 1, or it's a false negative. I mean, can you imagine if you were to go to the doctor and you're sore throat and they say, guess what, you don't have strep throat, but it turns out you did have strep throat, and you have to go back, and that's what a type 2 error is. Let's look at this bottom quadrant. If the results are not significant and the experimenter thinks the results are significant, well, we're going to accept null. Okay, and null said nothing was going to happen. We reject the alternative, and the study did not show anything. Now, let me stop right there because I put a frowny face, and I'm not sure I like my own little phrasing here. This points to something outside of the AP curriculum. Let me take a quick minute. There's what's called a publication bias in research. If you work for a university and you do a study and you spend, a year or years and some research dollars and a lot of time, and you find nothing significant, the problem is many research journals won't print that, and maybe your career takes a step back. The problem with that is proving something didn't work is oftentimes very important. So sometimes there's a bias bias against this kind of thing, but I shouldn't put the frowny face there. Accepting null isn't bad. It means that you proved something didn't work. Okay, we're moving on. Let's look at inferential errors. And that's anything that allows us or encourages us to link a small group to a larger group, or the link shouldn't exist. Okay, that means in statistics, numerically, we did not disprove null. Okay, and we call that a type 1. Think about that. We're still believing there's a relationship, there's a link between our small group and there's not in the large group, but there's not. That's type 1 or a false alarm. And so even though today's lessons are on statistics, I'd like it to link it to things you've probably been exposed to maybe a couple weeks or a couple months ago. In the cognitive psychology unit, think of the idea of heuristics. Okay, those are thinking shortcuts. Human beings are not very good at intuitively understanding statistics. If human beings were good at statistics, well, then nobody would gamble. Okay, because the odds are stacked against us. And a more unfriendly way to say it is lottery is a voluntary tax on those who don't understand statistics, right? So a heuristic is a thinking shortcut, and oftentimes we jump to conclusions. Think of the time your mother is worried about something that she saw in a magazine that's statistically rare, but it scared her. So that is going to steer her thinking. Okay, or another example is a teacher friend of mine said, think of Arizona, the state of Arizona and all the deserts. Think of the deadliest animal out there. And immediately our mind goes to snakes or scorpions. Well, the reality is it's just your average dog. That you're more likely to get bit by a dog than stung by a scorpion or snake. Cognitive biases, those are the results of, or those are also the processes of thinking, for lack of a better word, illogically. And logic follows the scientific method. It uses numbers, it goes slowly, and it analyzes results. But we oftentimes don't do that. So oftentimes we're going to make a jump, and the small group we think is connected to the larger group. Let me give you an example. It's a little more dark, a little more kind of sad on this, is the idea of outgroup homogeneity in the social psychology unit. And if you haven't gotten to social psychology, Mrs. Fenton and I will, towards the end of this review, touch upon some of the social psychology ideas. But the idea of outgroup homogeneity, I'll explain it in a quick phrase. Ready? They're all like that. It's really intimately woven into the concept of racism. So if you see behavior of someone who you think is different than you, and you think they're the outgroup, they're them, and they're doing behavior that's bad, you're going to take that one individual small sample group. And unfortunately, many people, all of us, I suppose, to some extent, are going to take that bad behavior of that group of person who's not like us and then say, oh, that's how they all are. That would be an inferential error. Okay. Okay, check for understanding. I hope I went slow enough. I know these are some difficult cognitive concepts to go through, so I'm balancing the idea of going slowly to give you hopefully you have an understanding, but I don't want to go too slow for time's sake, and many of us have seen this before earlier in the school year. But the main idea for inferential statistics is since we can't study 1 million people, we can't study 350 million people in the United States. So we're going to sample them, whether it's a presidential poll or a medical check or something like that. If that small sample, does that apply to everyone else? That's the main idea. Okay. Now we're on to our second part called descriptive statistics. And that's used to describe the population or sample that's right in front of us. Okay, so we just talked about what inferential is. It's used to study a group of people we can't study because it's too large. This is studying the smaller group that's right in front of us. Our old friend 3 types of central tendency always seems to appear in psychology textbooks and in the curriculum. But I'm not going to spend much time on this at all because I think if you're a junior or senior, you've seen this before in many years in your previous math classes. The mean is the arithmetic average of all the scores that are summed and divided by the number of scores. Okay, you get that. Median, the score that appears in the middle of the whole set as long as they're in order. So of course I circled 4 there, right? And the mode is the most frequently occurring score. And so here, since there's 2 would be the mode. Okay, this slide, even though there's not a lot of text or words on this, this is something that, heck, you might even want to take a screenshot of or take a picture of with your phone. This is really important. The median and mode are relatively unaffected by the presence of a few extreme scores. We call them outliers. But one extreme score can throw off the mean. I'm going to say that again. One extreme score can throw off the mean. And if you're a high school student, you might be really familiar with this. Let's say, for instance, you're a pretty good student. Your teacher gives you a series of quizzes, maybe one every week, and you, on average, you get an 80% on that. Sometimes you get an A, you get 100%, 10 out of 10. And then sometimes, well, you missed a few, you got a 6 out of 10, but they balance out. On average, you have a B. Well, let's look at what we call the concept of skewed data and outliers. So let's look at this one here, skewed negatively. Here is your quizzes, okay? On 3 different times, right here, you got a score of 80%. 2 different times, you got a score of 90. One time, heck, you got 100%, 10 out of 10, good job. And you're doing pretty well. Maybe something bad happened, and you got a 2 out of 10 on a weekly quiz. Well, look what happens. If you add up these numbers and you do the calculation with one bad quiz, one extreme score, your mean dropped. You now have a C average. Notice the mean and median are relatively unaffected by this one outlier. Over here, same thing on skewed positively. If you generally have a 80 average, got a 60%, 70%, heck, you got 100% here, 10 out of 10, great job. Now, one day your teacher offers extra credit and you nailed it, 14 out of 10. That one assignment will pull your grade from an 80% all the way up to a 90. The mean has changed to 9. The mean and median are still the same as an 8. So I hope that helps us understand skewed negative, skewed positive, and the idea that one extreme score will affect the mean, but not necessarily the mode or the median. Okay, descriptive statistics have graphic representations. This first one here is called a frequency distribution. It's just simply a table with X and Y. And you can imagine if I have X and Y, that's going to nicely translate into a graph where X is going to be the independent variable and Y is going to be the dependent variable. For example, a survey is taken at Northwest High School, let's go Jags, to compare weather conditions to student absences. Is there a relationship? The class of 15 students was asked how many times they were absent during the snowy month of January. The results were recorded as follows. Well, look, we have one person who missed 1 day, one person who missed 0 days, one person missed 4 days, okay, another person only missed 1 day, another person missed 1 day, someone missed, and I think you get the idea. So what we're looking at is we're looking at 0 days absent, 3 people. 3 people didn't miss 1 day. Of 1 day of whether it's snow or not, remember, we can't ascribe causality. We have no idea why they were absent, whether it was snow, whether it was not, we just don't know. But of 1 day, 6 people. So I think this helps us out. 2 days, there were 2 people. And this is a quick way, if you look at this set of numbers, this array of numbers right here, that's really, unless you have a savant-like ability, remember we talked about Kim Peek, I don't think you'll be able to make sense of that intuitively. So that's why table helps us out. Remember that X represents the number of days absent and Y represents their frequency, okay? Another way to look at graphic representations is bar charts and histograms, okay? When you look at a bar chart, one more time, on the x-axis is going to go down here. This is going to be the independent variable. Y-axis is going to be the y-axis is the dependent variable. Bar charts have categorical data. It means things that fall into categories that can't be measured. For instance, sophomore, junior, senior, or chocolate, vanilla, or strawberry, or DC, or Marvel, right? These are things that don't by themselves have a number attached to them. You can think of them nominal. They're name only. They don't have a numerical value. Bar charts, they don't touch. Histogram, ordinal. Think this through. You can put the data in order. Why? Because they're numbers: height, weight, GPA, income, those kind of things. The columns touch. Similarly to histogram and bar chart, The independent variable is on the x-axis, the dependent variable is on the y-axis. It's important that you can create and label parts of a graph. This actually was a talking point on an FRQ on an AP exam a couple years ago. Students actually had to draw in their exam book a graphic representation, and they had to figure out if it was supposed to be a bar chart or histogram. And I like this idea. By the way, this is going to be foreshadowing. Here we go. Ready? Because of what you're going to do kind of tonight's homework. I like this idea because if you can create the chart, that means you have an understanding of it beyond just answering multiple choice questions. Okay, so we looked at our graphic representations, we looked at a frequency distribution, we looked at a bar chart, and we looked at histograms. It might be worth your time to review those specifically. I don't want you to be able to define them because that's not what an FRQ does. I want you to be able to explain them. And that's going to be one of our tasks today on the homework towards the end. Okay, let's jump into more descriptive statistics, and we're going to talk about dispersion of scores. Remember, dispersion is a fancy word for just meaning spread out. Dispersions or measures of variability, how far the scores differ from the mean. I'll say that again. If scores are spread out, that means they're spread out from the mean. Low variability, look right here. It means the scores are not they're very close to the mean. High variability, of course, the scores are spread out. The range, this is a vocabulary word that you might need to know. If the height was 96, if the highest value was 96 and the lowest was 54, that means the range is 42. You just subtract, the lowest from the highest. That's going to give us our dispersion, how spread out they are. Okay. Let's look at our old friend, the bell curve. And we're going to spend a little bit of time here. You can see this in the AP psychology curriculum in the research unit and in the intelligence unit. So it's important to kind of get a deeper understanding here. Scores don't all line up on the mean. We know that not everybody is the same. Not all scores are the same. But they also don't fall randomly. If you get a big enough data set, they are going to fall into a pattern. We call that pattern a standard deviation. So when we look at our bell curve here, okay, it's important to know, just random trivia, if you don't know this, the average IQ score is 100. And if you look at these intervals, 100 to 115, well, that's interval 15. 15 to 130, it's an interval of 15. That means that our standard deviation for a standard intelligence distribution is 15. Okay, so from 85, within one standard deviation, from 85 to 100, 34% of any given, if you get a large enough data set, 34% of the people will have an IQ of 85 to 100. Of course, that's if it's a representative sample. I would imagine if we look at the IQ score of everyone watching this video, we are probably way above average, right, everyone? But if we were to look at other students, perhaps in a larger population, we're going to find that you are going to have, it's rare, but you're going to have people who have an IQ that is very low. It's rare that you're going to have an IQ of someone that's very high. It's important that you, unfortunately, you might, well, and we don't know what's going to happen with this year's AP exam, but it's important that you can talk through what this means. The further away from mean, well, it's only 14%. Further away from mean, it's only 2%. You get even further, 3 standard deviations away. Look how rare it is to have an IQ above 145. Okay, dispersion of scores. This is important, and I think you're going to see this coming up, foreshadowing alert on your homework for the end of today's video. A set of scores with a small range, meaning they're not very spread out, it's going to have a small standard deviation, and I think that makes intuitive sense. Okay, let's go into this concept of z-scores. For our purposes right now, we're going to say that z-scores are the same thing as standard deviation, okay? And they assess a scores different from the mean, distance from the mean. It's useful because it helps researchers compare scores from different studies with different standard deviations. Remember I said, what if you have 2 different researchers in 2 different universities and they study pretty much the same thing, but one has a sample size of 100, one has a sample size of 200, and you get the idea. If the variables If the variables are different, as long as those researchers put the results into a standardized way. And remember, I said standardization or statistics allow for a standard set of communication. It's like a common language between research results. Scores below the mean have a negative z-score. Okay, so if Clarence scored 72 on a test with a mean of 80 and a standard deviation of 8, his z-score would be -1. Okay, try to imagine it. 80 is the mean. Clarence scored below it on a 72. How many did he score below it? Well, he scored 8 below it, because 80 minus 72 is 8, which is the same number as the standard deviation. That means his z-score would be an exact -1. If Susie scored an 84 on that same test, what would her z-score be? I'm going to give a few seconds for you to kind of puzzle through it. Okay, well, I'll give you a hint. On the same test, if the mean is 80 and the standard deviation is 8, if you had an 88, your z-score would be 1. If you only had an 84, your z-score would be 0.5 or a half. Okay, let's practice this a little bit. If Daryl scored a 50 on a test with a mean of 50, what would his z-score be? Okay, and I think hopefully you would get a z-score of 0, because there's no difference, right? No difference from the mean. His score is not spread out, it's not dispersed. If Jane scored a 40 on a test with a mean of 38, so you know she's above, that means her z-score is going to be positive, and the standard deviation was 4, what would her z-score be? Well, if she had a score of 44, her z-score would be 1, but she's half of the standard deviation. It means her z-score would be 0.5 or a half. If Bill scored a 600 on a test with a mean of 700, that means he's below the mean. Okay, the question is, how far below the mean is he? Well, his standard deviation is 25. Well, the difference between Bill's score and the mean is 100. Well, that's 4 standard deviations below. Bill did not do very well on that test. Poor Bill. Okay, let's check for understanding. We threw a lot of numbers at us there. We're going to go back just a little bit while we check for understanding. And I want you to look at this chart. We looked at a standard deviation of 115. This would be a z-score of 1, z-score of 2, z-score of 3, z-score of -1. Remember, if a score falls in the middle, it's going to have a z-score of 0.5 or a half, or a score of -0.5. So that's our check for understanding. We're looking at standard deviation as a way to kind of make sense of this huge array of data, and a lot of it is not going to fall close to the mean. Most of it is, because that's what a bell curve is. Most of the scores fall close to the mean. Okay, that's our check for understanding. Here's our homework that I'm going to leave you with. It's a pretty big scenario. And, you know, you might look at this and say, oh man, I don't want to do this. You know what? It is worth slogging through some of this if you're unfamiliar with this, because remember what I said, psychology is science because of how we study it. Okay. I don't know what will be on the upcoming psychology exam, but I'm pretty sure there's going to be some research-based tidbits on some of the questions. As a result, much of what we're talking about over these last couple of days and today is fair game. I'm not going to spend our time reading all this. I'm going to leave that for you. But I hope that we, hit the pace, not too fast, not too slow, to go through some of this. And for some people, might be relatively complex statistical concepts. Thanks for watching. We hope you'll join us again. Be sure to complete the practice questions, make yourself do it, and we'll review the answer tomorrow in the next lesson. I will see you tomorrow at 4 o'clock. We'll review the answer in the next lesson.